All right, we're gonna try this, go through exam 3, do all the solutions. We're gonna do version C. So the first question is, what are the coefficients in front of this equation when we balance this? We've got cobalt 3 nitrate plus that ammonium sulfide, and we're going to make cobalt 3 sulfide and ammonium nitrate. So the ammonium is +1 charge, sulfide -2. That's why I've got 2 ammoniums per sulfide. Over here, I've got in my products an ionic compound, but it's 2 polyatomic ions. It's ammonium and it's nitrate. The ammonium's a +1, the nitrate's -1. So that's why they're in a 1-to-1 ratio there. So I'm going to look at a few different things and see what doesn't match or what contains, only some of the things. Maybe I notice in my cobalt 3 sulfide, I have 2 cobalts on the product side. There's 2 contained within that, but only 1 cobalt on the reactant side. So I could put a 2 in front of that, and that would make the cobalts balance. And then maybe I look at the sulfurs, the sulfides, the S's, and I say, well, I've got 3 of those on the product side, but only 1 on the reactant side. Well, I could put a 3 in front of there. So now my cobalt and my sulfur are balanced, and that shows how I make up that product, that CO2S3. But if I count nitrates on the reactant side, I have 6. And if I count ammoniums on the reactant side, I have 6. But fortunately, in the product that they make, when they combine in a 1-to-1 ratio. So it's not like I have 6 of one and 7 of the other, or 5 and 2 or whatever, and it's kind of hard to make them match. If I have 6 of each on the left-hand side, I can just put a 6 in front of that and get that many ammoniums and that many nitrates in the product side. And that should be the coefficient there to balance that one. All right, next, the combustion of hydrocarbon with oxygen produces what? So any kind of hydrocarbon, CXHY, so that could be, C2H6, it could be C10H22, it doesn't matter. When I react that with oxygen, the carbon is going to react with the oxygen and give me CO2, and the hydrogen is going to react with the oxygen and give me H2O or water. If I have just oxygen and I have a hydrocarbon with just carbon and hydrogen, if I get a nice clean combustion, I should always get CO2 and H2O as my products. All right. Give the net ionic equation for what reaction that occurs with aqueous potassium chloride and iron to nitrate. So there's my 2 aqueous products. I've got my positive and negative part of each. The potassium over here is positive. And then the chloride has a negative charge, and over here, the iron's got a 2+ charge, and we've got 2 of these nitrates with the -1 charge. So to see whether or not we're going to get a reaction and whether or not we're going to get a precipitate, I have to mix the positive part of one of these with the negative part of the other. So we're going to mix the potassium and the nitrate, and then do the same with the other one. Now we're going to mix the iron with the chloride. And if I do that, I'm going to get iron chloride, FeCl2, and I'm going to get potassium nitrate. But if I go and I look at both of these in my solubility table, what I'm going to find is each one of these is aqueous. So if I don't want to include any spectator ions, well, unfortunately, because both of these are aqueous or they're both soluble, they're going to give me 2 more aqueous ions. And I'm going to have K+, and that's going to be aqueous. And I'm going to have NO3, and that's going to be aqueous. And in terms of which ions I have on the reactant side and the product side, they're all identical. There are no solids, there are no liquids, there are no gases. There's nothing that comes out of solution. Every single thing is a spectator ion, so this would be no reaction. Or specifically, no precipitation reaction, and therefore no net ionic equation to write here. Because everything, like I said, is going to cancel. Cancel, 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 cancel. Write the balance equation for the reaction of gaseous ethane. So that's C2H6 with gaseous oxygen. So remember, oxygen's a diatomic molecule. So we're going to get CO2 and H2O. And then I need to start balancing them. And what I think I'm going to find is I could put, there it is, 2 there and a 3 there. And that's going to give me the 2 carbons that match, and then 3 times each of the 2 hydrogens is 6 hydrogens, so that matches, but it also gives me 1, 2, 3, 4, 5, 6, 7 oxygens. So I could put a 7 over 2 here, but halves aren't any of the options, so then to turn that from a fraction from 7 halves to a whole number, I'd multiply the whole thing through by 2, so I should have 2 C2H6 plus 7 O2 goes to form 4 CO2 and 6 H2O, which for this version, the correct answer there was A. All right, so we have a 4% sodium hydroxide solution. So that means we have 4 grams of sodium hydroxide for every 100 grams of solution. We are told that we have a 100, or we have in this case 185 grams of solution, and we want to know how many grams of sodium hydroxide is that. So we could set up this way, multiply these through, and what do we get here? 85 times 4 should be about 7.4 grams. You could also take 4 or as a decimal, 4%, 0.04 times 185, and you should get, the same thing. Either way, 7.4 grams of sodium hydroxide contained within 185 grams of solution. And you can think too, if there's 4 grams for 100 grams, 4 grams sodium hydroxide for 100 grams solution, if we had 200 grams of solution, we should have 8 grams. If we had 50 grams of solution, we should have 2 grams. So we're close to 200 grams, so we should see that we're going to get something close to 8 grams, which in this case we did. All right, here we've got an M1V1 solution. So I've got a concentrated solution, and we have a small amount of that, 21.5 milliliters, and we're told that we're putting some amount of, or that amount into a larger amount. So that amount of solution or the volume is going to increase noticeably. So if we take that small volume, 21.5, and we dilute it up to 765, up to a larger amount, like I said, we're going to dilute it, or we should end up with something that is a smaller concentration than what we started with. So we have our M1 and our V1 given to us. We have our V2 given to us, and then what we're trying to solve for is the M2. So if I do 9 times 21.5, I get 193.5, and technically this would be moles, because we have moles per liter, and we're taking that times or milliliters, so cancel out the volume term, and then we divide both sides by that 765. I guess we want it in molarity, or no, we should be able to, leave it like that. Since both units are in milliliters, and then they'll cancel. So there we go. So our M2 should be equal to 0.252 M. I can keep everything in milliliters like this, the 21.5 and the 765, or I could change them to liters. They just need to agree. So I could rewrite the 21.5 milliliters as 0.0215 liters, and then the 765 is 0.765 liters. I should get the same answer if I do that for both. There we go, sorry. And so this one, answer is C on this version. Maybe different number on a different version. Which is following is an acid-base reaction. So again, for an acid, I need something that leads with that acidic hydrogen. We're going to react it with, for us, in case, for now, just things that are strong bases, so things that have OHs. And we should see that we get water as a product. No, come on. There. So we got the, here we go. The acidic hydrogen here, and one of the hydrogens here, and those come together for the hydrogens in the water. And then we have the oxygen from the OH, making up the oxygen in the water. And then we have a salt, which is going to be the positive and negative components that are left, which is the Na plus and the Cl minus. So that should be a typical acid-base reaction, and really the only one of these three reactions given to us that follow that pattern. What's the percent composition of a substance? That's 14.68 grams of carbon, 3.7 grams of hydrogen, and 5.7 grams of oxygen. So we just want to know the percent composition. So we're interested in the part of interest over the whole thing. So if I add up all of these together, what I find is the mass of all three of the different parts coming together is 24.08 grams, and then I would take each individual part of interest. So for the carbon, it's 14.68 grams, so I would divide that by the mass of the whole thing, and I would see that that is 60.9%. I would do the same for the hydrogen. Now, just that part of interest divided by the mass of the entire compound. That's 15.3 or 0.4%. And then the oxygen, .7%. So, yep, only one available option there, A, on this version. What's the oxidation state of the chloride in ClO2 minus? So I've got only non-metals. So I've got to go to that table to see which ones takes precedence over the other. I know overall this molecule is a -1 charge, so whatever the oxidation state is on that one chloride and those two oxygens, it's going to end up being or adding up to a -1. Well, on the table, oxygen is higher than chloride, which is group 2A, so it's going to go fluorine, hydrogen, oxygen, 7A. Oxygen is high and it takes precedence. It has to have an oxidation state of -2. So in this case, I should find that the chloride is going to be a +3. Mixing of which pair of reactants will result in a precipitation reaction? So again, I'm looking at the positive component of one and mixing it with the negative component of the other. So the potassium for A is going to leave the sulfate and instead mix with the nitrate, and the copper is going to mix with the sulfate. So I have to look and say, is copper nitrate soluble, and is copper sulfate, or is potassium nitrate soluble, and is copper sulfate soluble? Yes, they are. With the barium, it's going to mix with the carbonate, and the sodium is going to mix with the nitrate. Well, anything and everything with sodium and or with nitrate is soluble. So I know the sodium nitrate will be soluble, but a lot of the carbonates are insoluble, and getting together with barium is one of the things that will give me an insoluble carbonate. So out of all the options here, you can double check the solubility table, but this one should be the only one that results in a precipitate. So mixing the barium nitrate and the sodium carbonate is going to give you that barium carbonate precipitate. Naval brass, so we've got naval brass is an alloy, so it's multiple metals combined. We've got 59% copper, 40% zinc, and 1% tin. So it's also a solution, not just an alloy. It's a solution of metals. We have a solvent, and in this case, solutes, because we have more than two components. The solvent is always the majority component. So copper is our solvent, and if it asked what our solutes were, those would be zinc and tin. What's the oxidizing agent in the following reaction? So we've got, all right, Mg, and it's a solid, plus Fe, and it's an ion, so it's aqueous. And then we go to this side, the product side, and now the magnesium is an ion, and it's aqueous. And the iron is now solid, no charge. So yeah, it's a solid. It would come out of the solution there. So rules for assigning oxidation states: magnesium, solid metal, no charge, free element in its naturally occurring state, 0. Iron, monoatomic ion, whatever its charge is its oxidation state. Same thing for the magnesium on the product side. And then the iron on the product side is now a free element all by itself, no charge. So it would have an oxidation state of 0. So the magnesium lost electrons and was oxidized. And the iron became more negative, less positive. So it gained electrons and it was reduced. On version C, excuse me, it's asking for the oxidizing agent. Other versions might ask for the reducing agent, but anyway. So for the oxidizing agent, it is the thing that facilitates reduction. Reduction is a gain of electrons. So for something to be able to gain electrons, something else has to be able to lose them. So the thing that is losing electrons, the thing that is giving them for that other thing to take them, is actually going to be the reducing agent. And then the oxidizing agent would be the thing that facilitates oxidation. So for oxidation to occur, something has to lose electrons and there has to be something there to take them. So the thing that's going to take them is facilitating oxidation and is the reducing agent. So for oxidizing agent and reducing agent, since they're helping to facilitate that process, they're always going to be the reactants, not the products. Because if we look at the products, they're no longer facilitating that reaction. The reaction's done occurring. So the iron, the 2+, the reactant iron, because it's being reduced, it's facilitating oxidation, and it's the oxidizing agent. And with the magnesium, because it's facilitating reduction, it's the reducing agent. All right, nitrogen's decomposed, found to have a ratio of 5 carbons to 7 hydrogens to 1 nitrogen. What they're really telling us here is the lowest whole number ratio, or essentially the empirical formula for this. We're also told that the molar mass, or the molecular weight of this, is 162.21 grams per mole. And they want to know what's the molecular formula. So what we have to do is find out how many times does that empirical formula or that empirical unit, that little basket containing the 5 carbons, 7 hydrogens, 1 nitrogens, how many times does that go into 162? So we need to find the empirical mass. So I'm going to take my 5 carbons times their mass plus the 7 hydrogens times their mass plus the 1 nitrogen. And what we're going to get is something around here. So I'm going to find out, like I said, how many times does that go into this? So 162.21 divided by 81.06, and we get 2.001, or pretty much 2 times. So I can fit 2 of those empirical formulas into the molecular formula. So I'm going to take my empirical formula, multiply it by 2, and now I should have C10, H14, and 2. Or for this version, answer D. Identify the spectator ions that occur when we mix potassium hydroxide and iron 2 nitrate. So again, we take the positive part of one, the K, and we mix it with the negative part of the other, and I get KNO3. And then the positive part of the second one, the iron, mixed with the OH, and we get iron hydroxide. And I go to my solubility tables, and I find that the potassium nitrate is soluble, but the iron hydroxide is insoluble. And they want to know the spectator ions. So the spectator ions would be the things that don't participate in that reaction, or the 2 things that, once they're dissolved and they dissociate, are going to be identical from one side to the other, which are going to be the potassium and the nitrate. Answer B on this version. Which the form would be weak acid. Okay, so acids need to lead with H+. So right at the bat, we can throw out sodium hydroxide. It's not an acid, it's a base. Out of our other acids, we have HCl, hydrochloric acid, H2SO4, sulfuric acid, and HC2H3O2 acetic acid. Well, for HCl, if you remember, we need to track those 6 strong acids, and that's one of them, so we can throw that out. And sulfuric acid is also one of our 6 strong acids, so we can throw that out. This one is an acid, and it's not one of our 6 strong acids that we need to memorize. So therefore, by default, it is a weak acid. Determine the molarity by dissolving 79.1 grams of lithium bromide in 750 milliliters of water, or to yield 750 milliliters of solution. So we want to know the molarity, and molarity again is moles over liters of solution. So we need to find out how many moles is that 79.1 grams of lithium bromide. So we're going to divide that by the molar mass of that. If we look that up, if we get what's 86.845. And when I divide 79.1 by that, we get 0.9108 moles. I need to put that over liters of solution. we have 750 milliliters of solution, or 0.750 liters of solution. And that should give us 1.21 molarity for our concentration. What elements undergoing reduction in the following reaction? So we've got zinc, solid, plus silver nitrate, aqueous, goes to form zinc, nitrate, and silver metal. So oxidation state on the zinc, free element, 0. Silver nitrate, we've got ions. The silver is going to be a +1. Nitrate stays as nitrate, so I don't really need to bother with it. But if I want, I would find that the oxidation state on the oxygens here are -2, and the nitrogen is +5. When we go over to here now, the zinc is a +2. Same thing, nitrate's unchanged, but we can find the individual oxidation states. We'll find the nitrogen is +5 on both sides, the oxygen is -2 on both sides, and the silver is 0. So they want to know what's undergoing reduction or what's gaining electrons, and in this case, it would be the silver. Each silver gains 1 electron, goes from a +1 to a 0, and is reduced. Give the complete ionic equation that occurs between H2SO4 and KOH. So I've got an acid-base reaction, and what I'm going to get then is 2 waters, because I've got 2 H pluses on the sulfuric acid. So I need 2 OHs to react with them. So I get 2 HOHs, and then I get my salt, which is going to be that potassium, the cation. It only has a +1 charge, so I need 2 of them to balance out the 2- charge on the sulfate. In terms of what ions we'd have, I'd have an H+ floating around here. I'd have the SO4-. I'd have 2 K+. I'd have 2 OH-. And then over on this side, the H2O is going to stay together as a liquid because it's not aqueous, but the potassium sulfate is ionic, so it will dissociate into those K+ and SO4 2- ions. So that's my complete ionic equation there. 4 aqueous parts on the reactant side, and 2 on the product side, and 1 liquid. Similarity of a 25% mass solution of NaCl. So if it's 25% by mass, that means we have 25 grams of NaCl per 100 grams of solution, and we want to know the concentration in molarity. So I want to get the units on the top to be moles of NaCl, and the units on the bottom to be liters of solution. I know we have 25 grams of NaCl. I can look up the molar mass of NaCl and divide that 25 by that. So 1 sodium plus 1 chloride should be 58.45. When I do this, I get 0.4277 moles of sodium chloride. And then we need to convert our 100 grams of solution into liters or milliliters. So I can take that 100 grams of solution and I can divide by the density. And see that 100 grams of solution should be 86.96 milliliters. And then it's just a case of putting molarity, moles over liters. And I get my molarity there, 4.93 M. The very last part, what's the empirical formula of a substance that's 60% carbon? So this is all by mass. So I'm going to assume a 100 gram sample and convert all my percentages into Grams. So we've got that many grams of carbon, hydrogen, and oxygen. And then I just need to convert it into moles. So for the carbon, I'm going to divide by 12, or more specifically, maybe 12.01. And I get 5. Hydrogen divided by 1.008. And the oxygen divided by 16. And we get 2.21875. So technically, my empirical formula is C5H 4.44 O 2.219, we'll say. So these aren't whole numbers, and I don't think any of our answers are in this format. They're not. So we need to get these into whole numbers. Fastest way is to divide them by the smallest number here. So divide all of them by the 2.219. And for carbon now we get 2.25. For hydrogen, pretty much get 2. And for oxygen, 1. So we're getting closer. Well, that carbon, that 2.25 as a fraction would be a 4th. So if I want to cancel that, what I would do is multiply the whole thing through by 4. And then that 2.29 becomes, or 2.25 becomes 9. Our 2 becomes 8, and our 1 becomes 4. So we should have C9H8O4 as our final empirical formula for that particular compound. So there's the exam. Again, if you have any questions, if you think there's an error, please stop by my office hours. And I will gladly, go through any part of this with you. I will pull your Scantron. Otherwise, I'll see you in class Monday or Wednesday.